Welcome to the first chapter in the TI Precision Labs series on stepper motors. My name is James Lockridge, and today I will discuss the basics of stepper motors. Many applications use stepper motors because they allow for fine position control without requiring external sensors or complex control algorithms. Sometimes this is called open-loop position control. The stepper motor can provide continuous motion or maintain a fixed rotor position depending on the system requirements. These features make steppers easy to implement and a low-cost solution for system designers. Before diving deeper into the topic of stepper motors, I will review where they fit among other common motor types. Brush DC, brushless DC, and stepper motors are the most common types of motors powered from DC power sources. Brush DC motors have a winding on the rotor. Brushes, made of metal or carbon, energize the winding through a commutator on the rotor. As the rotor rotates, the commutator changes the direction the current flows through the windings. When the current changes direction in the winding on the rotor, the polarity of the rotor's magnetic field changes. The commutator ensures the polarity of the magnetic field on the rotor always opposes the magnetic field created by the magnets or windings on the stator. This creates continuous motion in the brushed DC motor. The brushless DC motor contains permanent magnets on the rotor and windings on the stator. This is opposite from the construction of the brushed DC motor. For the brushless DC motor, there are no brushes or mechanical commutator. Commutation is handled electrically. Typically, brushless DC motors have 3 phases, which create motion when energized in the correct sequence. The animation and image show an outrunner motor with rotor magnets positioned like a shell around the inner stator windings. Stepper motors are similar to brushless DC motors since they also handle commutation electrically. Stepper motors typically have only 2 phases, however steppers with 3 or more phases exist. The rotor in a stepper motor moves in discrete positional steps depending on the magnitude and direction of the currents in each phase winding. Stepper motors come in one of 3 main types: permanent magnet, hybrid, and variable reluctance. The permanent magnet stepper motor has a permanent magnet on the rotor. The winding coils are oriented around the same axis as the rotor. Rotor teeth on the stator help to direct the magnetic field from the rotor to interact with the windings on the stator. The magnetic poles on the rotor are oriented parallel to the rotor's rotational axis on the surface of the rotor. Rotor motion occurs as the permanent magnet moves to align with the magnetic field of the energized winding. The variable reluctance motor does not use any permanent magnets. The rotor is made of the same magnetic steel as the stator. The variable reluctance motor gets its name because the magnetic field causes the rotor to move to a position where the air gap and magnetic reluctance are minimized. The difference in reluctance is created by the shape of the stator teeth on both the rotor and the stator. The variable reluctance stepper motor typically needs at least 3 phase windings to effectively control the direction of the rotor rotation. The hybrid stepper motor gets its name because the rotor contains a permanent magnet while the stator and rotor have rotor teeth just like the variable reluctance stepper. The permanent magnet on the stepper is oriented with the magnetic field in the same direction as the rotor's rotational axis. This is different from the construction of the permanent magnet stepper motor. The rotor teeth on the end caps on either side of the magnet redirect the magnetic flux path outward from the magnet to the stator teeth to maximize the magnetic field's interaction with the windings. Of the 3 motor types, hybrid motors are the most common, and variable reluctance motors are the least common. Permanent magnet and hybrid stepper motors typically have 2 phase windings, although in some cases they may have more. Hybrid motors typically have smaller step size and higher torque than permanent magnet stepper motors. Hybrid and permanent magnet stepper motors come in bipolar and unipolar winding configurations. For bipolar motors, H-bridges allow the current to flow in either direction through the winding. The direction of the current determines the polarity of the magnetic field created by that winding. Unipolar motors only need low side or high side FETs to drive the current in one direction through the windings. The winding of a unipolar motor has a center tap that can be connected to ground or the motor supply. Rather than driving current in two directions to change the polarity of the stator magnetic field, the coils for a particular phase are wound in opposite directions to achieve the change in magnetic field polarity needed to continue moving the rotor. Unipolar motors can be driven like bipolar motors if the center taps are left unconnected and the coils are connected to a bipolar stepper motor driver. Integrated stepper drivers control rotor position by energizing the stepper windings in a particular sequence. In this example, the microcontroller sends a pulse to the stepper driver to indicate that the stepper rotor should move to the next position. When the stepper driver receives the step pulse, it energizes one of the phase windings in the sequence. When it receives the next pulse, it energizes the next phase so the rotor can continue moving. The H-bridges integrated in the stepper driver control the current in the phase windings in both directions to change the polarity of the windings and continue moving the rotor. If the microcontroller stops sending step pulses, the rotor will remain stationary and aligned with the magnetic field of the energized phase. Integrated stepper drivers often implement additional features for protection, microstepping, and stepper tuning. For more information on stepper motors and TI integrated stepper drivers, please visit the stepper driver page on TI.com.